So hi, I'm Francis. I'm doing my master's degree at the University of Sherbrooke's Robotics Lab. So our focus is to enhance autonomy in... does the mic work?
Yes.
Okay. So enhance autonomy in robots cohabiting with humans. So my part was to integrate the episodic memory into our robotic platform. And I use adaptive resonance theory to do this. And that's what I explained.
Probably you should hold the mic closer to your mouth.
Closer. All right. So the main goals in autonomous robot, what we want to do with our platform, here is IRL1, so the robot our labs has developed. We want those kind of robots to be able to decide on their own on what, when, and how they can fulfill their task in the most efficient way and productive manner. We also want them to be to evolve over time, so to be able to adapt their behaviors to new situations. And also, they must be in a dynamic environment with other robots. And so how does the episodic memory will help going towards these goals? So the role of episodic memory is to organize the robot's experiences from his own perspective. So the robot will be able to recognize similar situation, and if that occurs, he can adapt his behavior, change his decision making based on his past experiences. So here is our proposed model. It's inspired by a previous work from another lab. So they validated a similar model of episodic memory in a video game environment. However, in robotics, sensing the environment is very different. The sensors are less reliable, and often the perception comes asynchronously from different modules. So we needed to develop a short-term memory at the bottom to synchronize all the information and get a complete picture of the context of the robot that we feed to our episodic model. So it's composed of 3 layers. The input layers is divided in different channels. So in each channels, it gathers different type of information. So in this case, we have the location, objects, the people the robot recognize, his behaviors and his emotions. So this is it represents the context of a situation. So there is an arc network between those 2 layers. So to categorize an event, so a current situation, based on the pattern of all the input layers, and also another one between those 2 layers categorizes the sequences of events. So we keep a trace of every activation in this layer, and we try to recognize it as a pattern. Also, a very important feature of our model is we wanted to favor the most relevant episode into his memory, because the memory learns everything the robot experiences, but some of the things are more important for the robot and for his decision. So we use an artificial emotion module. Artificial emotion module to influence the system to favor the most relevant information. I will get in more detail later. So this is the experiment we did with our robot to validate the model. So it's an object delivery scenario. In the first picture, the robot recognizes a person and an object, a book in this case. Then the robot asks to give the object. Then the robot goes to a predefined room to deliver the object. And in this room, you will randomly search for a person to give the object. So this is the place we want to optimize. We want the robot to go directly to a person without wandering around. So here he delivers the object, and then learn the whole episode. And from that point, he comes back to his initial point. So as I said, there are important parameters in this model. So the first one is the vigilance threshold. So this is the threshold for pattern matching. We need to adjust these parameters according to the artificial emotion, so that the most relevant episodes will be recognized easier. So we lower this parameter for important episode. And also the learning rate, beta, is used for the stability of the model. So an important episode for the robot will stay stable until his memory longer in his memory. So we lower, once we did the learning the first time, the future learning won't affect the initial learning. So that's the logic behind the emotions. So I'll get through briefly the mechanics of the model. So here the first step is the encoding. We represent the context in the input layer. So in this case, we are in the first room with a book and a person. Then the activation step of the art network. So basically, it's a competition between every node in the event layer. We choose the one with more similarity. And for the next step, we compare the chosen neuron with the threshold. So there is a threshold associated to each neuron. So there is not a common threshold for all the layers. It's because some of the events are more relevant, so they will be recognized easier, even if there are some differences, and other one will be less relevant. So if we are above the threshold, we choose this neuron for learning, else we can create dynamically new neurons in this layer. So once we choose this neuron, we learn and we adjust the weight between the two layers according to the beta parameter. Then, after a few recognition, we have a sequence. So every time we recognize a new event, we will lower the other activation to have a relative order between every event. And so every time we have activity in the event layer, we will try a recognition on the higher level. So we will, before the task is even done, we want to recognize the ongoing sequence. So if it occurs, we will have a prediction on the upcoming events. So the same equation between those two layers, the same equation are used. So once we recognize the ongoing sequence, we can read out the episode and look at the differences. In yellow, you see the differences are the prediction. So this prediction can be used by other modules of the cognitive architecture. So we read out those nodes with the input layer to get all the information we need. And finally, when the task is done, we learn the sequence, we adjust the weight, And we also adjust the two parameters associated to this episode. Like I said before, the artificial emotion module will, if the episode was highly emotional, we lower the vigilance threshold, so it will be recognized easier the next time. And also, we lower the learning rate to have more stability for the future events won't affect this episode as much. So briefly, the artificial emotion is a really simple module that we need to get better, and it's generated based on how the robot is able to satisfy its intention. Like, for example, when the robot tries to go from point A to point B and we block its path, the robot is not able to satisfy its intentions, so anger is generated over time. Here's the schematics of our architecture. So from the sensors, we have a perceptual module to recognize object, person, etc. that sends asynchronously information to a short-term memory, then feeds the episodic memory. And once we have predicted events, we send it to our task. So in this case, the object delivery that activate different behavior based on priorities, that sends comments to actuators. And also, those behaviors send information to our artificial emotion module that influences the episodic memory. So we validated our model in different conditions. Basically, we wanted to see if the robot was able to make prediction and if those predictions were useful. So I will explain the three of them. In this case, we tested the object delivery scenario 10 times, and we wanted to see if the robot can recall the episode before it was over, and then use the last delivery location as his new destination. So here you see in yellow it's the initial path, so he wanders around a little bit before arriving to the destination. In green, it's where the robot uses his episodic memory to get directly to the location. So X is where the robot recalled that it's something he already did. So he used the prediction to go to his destination. And in blue, it's when the path is pre-programmed, so he doesn't use his memory. So in this case, we wanted to see if the robot can separate different semantic scenarios. So we show him 3 different objects to deliver to 3 different episodes, and as expected, you see here there are 3 at the end of 10 trials. There are only 3 episodes in memory. So the robot uses its prediction to get to the right delivery destination according to the object. And in this case, we tested when the emotion was at its highest value. So we blocked the path of the robot, so he wasn't able to, so anger was generated. As you can see here, all the recalling of the episode was done very early in the scenario, in the initial room actually, and from that point, the robot goes directly to the delivery destination. So the recalling was easier because of the low threshold of this episode in this memory. So finally, we developed a spatial temporal recognition system used as an episodic memory for autonomous robot, and we dynamically adjust some parameters to favor the most relevant episodes in this memory. Now we need to integrate this model in a more complex cognitive architecture or in a more complex robots to have different tasks to test. So that's it. Thank you.